Hello everyone, welcome back to my channel. In today's video we'll be looking at the elastic potential energy of a spring. So before we get to it, don't forget to like and subscribe to this channel. Alright, let's discuss what the elastic potential energy is. Now, if you look at the elastic potential energy, PES, the elastic potential energy is simply just the energy stored as a result of applying a force to deform an elastic object. The energy that is created is stored until the force is removed and the object springs back to its original shape, doing work in the process that is. The deformation could involve certain procedures such as compression, tension, or even twisting the object. Now, to clearly understand this, it's best to look at several examples. But to start with, we'll look at the equation that denotes the elastic potential energy of a spring. So elastic potential energy of a spring, PES, is simply equal to half kx squared. Half kx squared. Now in this formula, be mindful of this. The k represents what we call the spring constant, what represents the stiffness of a spring. X represents the extension, change in length of a spring. Now, what I want us to do is to quickly look at some examples that will help us understand this. Alright, let me just change color for explanation purposes. Alright, now look at this. It says a spring of an extended length of 10.5 centimeters is suspended vertically from a fixed point as shown below. A mass of weight 2.7 is hung from the spring as shown below, causing the length of the spring to change from 15.2 centimeters. An additional force F is added and extends the spring to another length of 20.0 centimeters as shown below. So we're having this, which is showing us an extended length, and we're having this part and that part that shows us the two extensions that we had. Now, S says for the extension of 15.2 centimeters, calculate the elastic potential energy of the spring. Take the spring constant K to be equal to what? 60 newtons per meter. Alright, let us get to it. So, the first thing we're supposed to do is to write the formula for the elastic potential energy, which is PES, being equal to half kx squared. Now, in our equation, we need to collect data and ask ourselves, what is the value of k? We know that k is 60 newtons per what? Meter. X is the extension of 15.2. Now, what extension was created out of this system here? So remember, extension is simply the change in length. So we have length final minus what? Length initial. So extension is equal to length final, which is 15.2, minus length initial, which is 10.5. So the extension, if you do your math right, will be 4.7 centimeters. But extension should not be in centimeters, but in meters. So we divide this by 100, and we'll have our final extension to be equivalent to 0.047 meters. And this is our extension. Upon doing this, the only thing that we need to do is to plug back in the formula. So we say PES is equal to half, the value of K is 60, the value of X is now 0.047 squared. So PES, if you compute this on your calculator, you do the math right, you get your final answer to be 0.06627. If we round off, the elastic potential energy for the extension of 15.2 centimeters will just be 0.07 joules. As simple as that. Let's move on to another example. Say we have this. Alright, so now it's the same question, but here they're saying for extension of 20 centimeters, calculate the elastic potential energy of the spring. So if you want, you can pause the video and attempt to do this work on your own. Alright, let's begin. Like we did, first write the formula. So PES is equal to half k x squared. And upon doing this, all we have to do next is to collect data. What is our k? Our k is simply the spring constant, which is given to be 60 newtons per watt meter. Our extension should be here, the change in length of this action in relation to the unextended length. So it should be length final minus length initial. So extension is equal to length final, which is 20.0, minus the initial length, which is 10.5. And if you compute this, you would end up having 9.5 centimeters. Extension can never really be in centimeters unless specified. So we convert to meters, so we divide it by 100. So extension will be equivalent to 0.095 meters. Upon having this value, all we need to do next is to plug back in our formula. So elastic potential energy of the spring is equal to half k is 60 and the extension is 0.095 squared. If you compute this on your calculator, then the elastic potential energy of the spring for the extension of 20.0 centimeters will be equivalent to 0.27075. If we round this off, then the elastic potential energy of the spring will just be 0.27 joules. As simple as it is. Now the other question that might be given to you is where they would ask you, say, to calculate the change in elastic potential energy given this systematic question. So in this scenario, all we have to do is literally the same, but since we have two extensions, what we'll do is this. We'll take the formula as it is, but where there is extension x, we'll write it as a change in extension. So the elastic potential energy of the spring will now be equal to half k change in extension squared. So this is the formula that we'll be working with. Now this implies that the elastic potential energy of the spring is now equal to half k open brackets extension 2 squared minus extension 1 squared. Now remember that we need to find this extension separately. This is extension 1 and this is extension 2. So this is extension 1 and this is extension 2. Let us now collect data and ask ourselves, what is k? K is 60 newtons per watt meter. What is extension 1? Extension 1 is the change in length of the final and the initial. So extension 1 will be the final, which is 15.2, minus the initial, which is 10.5. And this will give us something as 4.7 divided by 100. We get our final extension 1 to be equivalent to 0.047 meters, like that. Then extension 2, length final minus length initial. Extension 2 is equal to length final, which is this one now, 20.0, minus initial, which is 10.5. And if we compute this, we end up having a 9.5 divided by 100. Extension 2 is equivalent to 0.095 meters. Now upon having this, all we have to do is to plug back in the formula, this one here. So we say the change in elastic potential energy is half the value of k, 16, and these extensions, extension 2, 0.095 squared. Let me not, okay, it's fine, just like this, minus extension 1, 0.047 squared, like that. So if you compute this on your calculator, you'll be having the change in elastic potential energy to be equivalent to 0.20448. Rounding this off, the elastic potential energy is equivalent to 0.20 joules. So the change in elastic potential energy for extension 2 and extension 1 of this system that we have here is simply 0.20 joules. Another way you can do this is by finding the elastic potential energy of extension 1 and extension 2, then finding the difference of that. Alright, thanks for watching. This is Mr. Hussein Mosapi. Don't forget to like and subscribe to this channel. If you have questions, kindly contact me on WhatsApp, the number that I've indicated there, the number that I'll put in my description. Alright, remember to strategize before you become a statistic, and let's try and push for that A+.